Hello everyone, my name is Sayyed Uwais Alisha and I am a software engineer. My mostly strength in a backend engineering. So I am Ruby tool developer mentee in the Spring 2025 LFS mentorship with RISC-V International. So I start my journey in RISC-V from 2022 and I start an open source contribution from 2023. In this talk, I will share my working on the RISC-V International, so what it is, why it matters, and how contributing in strength my backend engineering skill and my understanding in open source contribution. So this work done as a part of LFX mentorship under RISC-V International in spring 2025. Like I say, I worked on a RISC-V unified database, which is also called a UDP, where I am role of Ruby tool developer as a mentee. So I was fortunate by mention the name of my mentor. My two main mentors is Paul Clark and Derek Hoare, which helped me a lot in the journey. And I mentioned another name which is not my official mentor from like LFX or RISC-V. Is also an RISC-V contributor, but he's helped me more. His name is Afonso Oliveira. I name correctly. So these three mentors helped me a lot in the journey, whose guidance played a major role, major role in a professional or technical growth throughout the mentorship. So what is the RISC-V Unified Database? What is UDB? So the RISC-V Unified Database is a single machine readable source of RISC-V architecture. It centrally describes extension, instruction, CSRs, controls, and strategy register, profile, and manual structure way. Okay, UDB serves the foundation for specification-driven tooling, like enabling both human readable documentation and machine consumable due to generating the same source. Why the RISC-V unified database is essential, like before what we face a problem and what and after the UDB what the problem is solved. So basically before UDB, RISC-V specification was fragmented across the documentation and repositories. Most of the information was not machine readable, which made validation, automation, and compare difficult. So UDB address that is by providing structured, validated, and version architectural data, significantly reducing duplication and ambiguity, which ensuring consistency across the ecosystem. So UDB structure and workflow. So there is, I think, four main part is YAML specification, second is schema enhancement, UDB tooling, and fourth is containerized workflow. So basically, UDB store architecture data using modular YAML specification files. This file is validating using schema, ensure correctness and consistency. So Ruby-based tooling and backend process is due with this data to generate artifact and everything run in containerized environment, and using the rake and the .do wrapper. So another thing that the workflow ensure reproducible and reliable output across the different tool and platform. So ideal is a descriptive language which is first time I'm learning in the during the mentorship, where mentor helped me what is ideal and how to deal with it. So I span it. UDB uses the ideal, which is description language with executive instruction and CSR behavior. Ideal is strongly typed and designed specially for RISC-V, allowing specification to be precise and unambiguous. It supports configuration dependencies, behavior, and enable advanced analysis such as symbolic execution and data and dead coding pruning. This make ideal a critical bridge between specification and implementation. And I am like I give more time in ideal for learning and how to deal with it. Like I'm first time learning ideal in this mentorship program. So my contribution in LFX mentee, as a mentee, I'm writing many YAML file. Like first time, I understand YAML, what's YAML, but I'm first time writing YAML for RISC-V specifications and many documentation. I am doing working on a Ruby tool validation and on logos and many of the things. And the one of one of the major thing is bug resolving, because this is a big product, or like big repository, so there's multiple bug. So I love to resolve, and my mentor helped me and assign the tasks, and I solve all the things. And that, yeah, I mentioned, I'm working on an ideal at first time, understanding what's the ideal, reach out my mentor and another mentee, and like landing what is ideal. I did new things which help me to grow more in future in the RISC-V. So in the end, I would like to say that LFX mentorship strength my how to leverage strength my backend engineering skill and understand the RISC-V, which is helped me a lot, like how to contribute in an open source. Like, yeah, I'm working on open source like 2 to 3 years before, but how to work in a team, like mentor help a mentee, and mentee communicate mentor, and communicate with other mentee with globally environment, like which is help us learning, and which help us a lot of in the RISC-V. So this is helped me to take like to select in my job. Like I am working on a recently in as a backend engineer in a science technology. So the LFX give me a like major part for selecting, like now I am selecting as a job or working on an industry or another thing. I am also associating with the RISC-V and working on RISC-V. So in the below we are I attached the link of LinkedIn and GitHub, so all of you can reach out me, like of any listener, if you want to work on a RISC-V, understanding the how RISC-V work, and any query about UDP and any other things about the career, about LFX. So reach out to me, and in the end, thank you for your listening. Thank you very much.
Hello everyone. My name is Hafsa Shoaib and Linux Foundation Mentorship 25 Looks 590. And today I will be presenting our work titled Implementing RVP version 1.0 Floating Point Vector Extensions in the Nucleus RV core. First of all, I would like to thank the Linux Foundation LFX program and the RISC-V community for providing this opportunity and platform. This project was by MER UITU, Microelectronics Research Lab, UIT University, and was completed under the guidance of our mentors, Dr. Farhan Ahmed Green and Shazib Kashif. Now, let's move towards the speaker about me. I'm a RISC-V researcher and a hardware designer with experience in vector architectures, post-quantum cryptography, and open source hardware development. I have worked extensively with Chisel and System Verilog and contributed to several projects such as Adhestia, Passban Core, and Nikita. As part of the Linux Foundation LFX mentorship, my focus was on implementing RVV version 1.0 for defined vector extensions in the Nucleus RV core, strengthening its vector computation capabilities. Now, let's start with the motivation. First motivation, of course, modern workloads increasingly depend on the vectorized floating point computation, especially in AI and machine learning, scientific computing, DSP, and graphics as well. So while RISC-V vector extension version 1.0 provides a powerful and scalable model for vector computing, many open source cores still lack complete floating point vector support. And third one is, of course, in particular, the existing Nikita vector coprocessor supported integer vector operations but had limited floating point execution capability. Our work addresses this gap by extending Nikita to support RVV version 1.0 floating point instructions, bridging the gap between them. Next is our objectives of this mentorship. Of course, based on this motivation, our mentorship had 4 key objectives. First, to integrate floating point vector sessions support into Wikita. Second, to extend Wikita to support FP operations. Third, to ensure seamless integration with the Nucleus RV core. And finally, to maintain the compliance while keeping the design scalable and parameterized using Chisel. Next is our Nucleus RV core. Nucleus RV core is a Chisel-based RISC-V processor. It's a 32-bit RV32 core supporting the IMF, C, and V extensions with a 5-stage pipeline architecture. The design is fully parameterized and configurable, making it suitable for research and SOC integration. Nucleus RV also serves as a base core for the SOC now SOC generator, and its verification is performed using RISC-V test cases. Vegeta integrates with this core to provide vector execution support. Next is going to be our Vegeta vector coprocessor. So Vegeta is an RISC-V version 1.0 compliant vector coprocessor written in Chisel. It is designed for in-order RISC-V cores and cannot operate independently without a host core like Nucleus RV. Architecturally, Vegeta features a configurable VLAN and a 4-stage pipeline execution model. It supports vector-to-vector, vector-to-scalar, and vector-to-image instructions. Next is RISC-V version 1.0 floating point vector extensions. Of course, RISC-V version 1.0 extends scalar floating point operations to vector registers. Instead of operating on scalar FP registers, these instructions operate on vector registers V0 to V31. The extension is compliant with IEEE 754/2008 and supports vectorized floating point arithmetic comparison conversion between integer and floating point types. Our goal was to correctly implement these semantics inside Vegeta. The image shows the list of all floating version RISC-V version 1.0 floating point vector instructions, including the single width, floating point integer convert instructions, single width FP add and subtract, floating point multiply and divide, square root, min max, compare instructions, single injection instructions, classify, move, merge, and also the single width floating point with just reduction instructions as well. So these are all the list of vector floating point instructions. Next is we have the Berkeley Hartford Library. The Berkeley Hartford Library is to implement the floating point operations. We use that library. The image illustrates the Berkeley Hartford Library components we used. Hartford is a Chisel-based floating point hardware library that internally uses a recorded floating point format. This allows efficient handling of corner cases such as subnormal numbers while abstracting this complexity away from the designer. Hartford provides floating point arithmetic units as well as conversion modules between IEEE 754 and the recorded format. Next is we have the integrating vector floating point into Vegeta. So of course, to integrate floating point vector support into Vegeta, we introduce several new modules. First, we introduce the vector floating point parameters. Then we have the FP ALU object, and then we have the vector floating point ALU. The parameter one defines floating point format parameters like exponent, width, and significant size. ALU object encodes RISC-V floating point instructions, ALU control information fields. Vector floating point ALU performs floating point execution, supports masking, till undisturbed behavior, and integrates Hartford operations as well. And all the instructions of all computation and arithmetic as well. This design keeps the implementation modular and scalable. Next is the execute stage. The floating point vector execution is integrated into Vegeta's execute stage. This diagram shows the execute stage of Vegeta where floating point ALU is integrated. The design allows floating point vector extensions to reuse Vegeta's existing pipeline structure with minimal disruption and allows FP vector instructions to flow naturally through Vegeta's existing pipeline. This is the code of parameters, vec FP parameters, where we define the bias, exponent width, and sine width. And next we have the ALU objects where all the ALU control objects are defined. And then we have the ALU module in which all the coding of the computation and arithmetic computation are going on and are done. Next we have, of course, verification. Any design needs verification to prove that it's right. So first of all, verification was done incrementally. We begin with instruction level testing using the Spike simulator, followed by step-by-step validation of individual floating point vector instructions. Next, we go for, of course, the compliance test as well to ensure that we match the compliance test cases as well. For compliance, we use the MPROS RISC-V test suite to be verified RVV version 1.0 behavioral correctness across multiple configurations, including VLAN means the vector length is equals to 256, ALMA values are 1, 2, 4, and 8, and CU of 32. This ensured that our implementation adheres strictly to the RVV specification. Next, of course, the experience and key takeaways. To conclude, this project reinforced how critical open source IPs are for the future of open silicon. Chisel enabled rapid, scalable hardware development, while RVV demonstrated the power of flexible vector abstractions. This mentorship significantly strengthened my skills in architectural design, auto debugging, and translating the specifications into working hardware. I would like to sincerely thank our mentors, the Linux Foundation, and the RISC-V community for their seamless support. Thank you so much, everyone, for your time.
Hello everyone. I'm Usman Akiemi, and I'm here to talk about my project at RISC-V Mentorship Program. So the topic for for my presentation today is building a machine readable taxonomy for RISC-V instruction encoding. Let's start. So basically, who am I? I'm basically Usman Akiemi, as I said earlier, and I'm a final year student of computer science and artificial intelligence at Flagship University, India, and I've been involved in different open source projects, including RISC-V, systemd, where I created a new unit test framework, and also I'm a Git contributor, and I had the opportunity to present one of my projects at the last Git conference, and I also I did my last internship at under Google Summer of Code at OSIPI, where I built a medical imaging pipeline for the project. I love Linux and I love working with system softwares, developer tools, and my software journey has been around open source. So as I said earlier, I basically did my own mentorship, RISC-V mentorship, in the spring of 2025, and my mentor were Paul Clark, Direkova, and Afonso. I hope I was able to pronounce it well. So I also had a link for you to access RISC-V UDB, which is Unified Database, RISC-V Unified Database. So basically, what is UDB? Basically, we have different sort of manuals, RISC-V manuals, and they're all scattered around, right? So you have RISC-V ASA manual, you have ASM manual. These are all scattered around. Sometimes it's so hard to find it. You want to probably look for something like RISC-V ISA manual. Where should you go to? So that's what UDB tried to solve. Try to be the golden source of truth for all team RISC-V information. So if you need any form of specification, RISC-V specification or information or docs, UDB is the golden source of truth for that. And I was able to extract this particular slide from this this was a presentation by one of my mentor, Afonso, and I already had the YouTube link. You can always check. So apart from that, there's also another important thing which UDB does. So apart from being this golden source of truth, it also does a lot of other things. But one important thing is, we can use it, as I said earlier, it's for manuals, RISC-V manuals. It can also be used for generating docs, certification document also, right? And also you can use it to do instruction set simulator, right? Also cross verification tools, checking against LLVM, and yeah. So I already talked about like a certificate. So this is also like an extract from Afonso, and you can also check the full video to sort of understand what are the other things that you can get about UDB. So basically coming to my own project, so this is basically like two different instructions, but both of them are actually R-type instructions. If you actually see the layout, they sort of have different layouts. There's RS2, there's RS3 here. So, and you can see these have like, so these are like, despite the fact that they are the same type under RISC-V manual, right? But ISA manual, but like they have different structure. So now what is actually the problem? As I said earlier, like RISC-V didn't did not tell us about like these differences. This is just like two examples which I gave. If there are actually like different R types with different structure. So the ISA manual, the RISC-V ISA manual descriptions, they are not precise enough. So it's hard to like create tooling or automations around that, right? Because it's like it's ambiguous, right? So you can't create a particular function for just R type, because there are a lot of R types. You can't create one single like tool for something like I type or other kind of types, because they're like ambiguous. So it's hard to like create an automation tool for that. So really encoding is reused bits in different ways. You can see like different bits are used for different purpose, like are sort of used for different purpose. There's a register 3 here, but it's not here. So sometimes, like, despite the fact that they're like the same types, they have different different use of bit. As I said, also like automated validation and documentation we need strict definition for that. It can be ambiguous, but the RISC-V instruction set is not able to like instruction manual is not able to like tell us like all this. So LLVM also like use different like like it's actually like split all these instructions into like more formats, like it's not just only R type, it's like giving different format. Like, so these are the problems. The RISC-V ISA is not straightforward, it's ambiguous, but we also need, and we want to like create an automation tool for this, for certification generation, for docs, and for more other purpose. But RISC-V ISA specification is not it is ambiguous. So what's our main solution? So our main solution is basically like to create like a definite schema for types ops code, and also to sort of introduce another something we call subtypes, which is basically like trying to like these particular two types that we have, can we give it different names, and can we sort of like create a new subtypes from these two from different structures based on whatever I see. So so this is for easy verification of instructions, doc generation, and for tooling. This has been done, it has been completed, but like there's still a lot of updates that can be done to this. Also like creation of creating new subtypes, so this is still ongoing. And also like converting all the instructions in the so we already have all the ISA instructions in the UDB, so we have to convert it to use the same to use the new schemas and the new subtypes which we just created. And so going on, so this is an example of what we have done. So this is basically an I type using the new schema that we created. This is basically trying to like define the I type. So we also like created the schema in such a way that it's easy to sort of like create an automation tools around it. So, and we are basically like using YML file, right? So this is the I type, and this is basically like one of the subtype which I created, which is IXX. And if you look at it, it's basically like just using it's inheriting from the I type instructions, and and it's also like defining like what are the structures, what are the things that you expected. So it's expected that we have like a register 1 register and destination register, right? And also like some immediate value, immediate bit, right? And it's also like each of them are referencing each other. So that's one of the purposes. It's possible that we have like another types or subtypes that is also like referencing immediate. So this is for result. The schema works in such a way that it's reusable, right? And easy for like automation and to generation. So what are the key takeaways? Of course, like RISC-V instruction classification is harder than it looks. We like for just like this particular types, you have like different types, right? So this is just what I'm showing you. For I types, you have like different format, like the bit are used for like different purpose. So it's RISC-V instructions are like harder than it looks. So but like from types you can subtypes capture like so what you are trying to do right here is that types is sort of like give like a structure like to a sort of shape that okay for our type it's registered to register instructions, but like subtypes actually go more deeper and capture what is actually going on, what is going on in the scenario that we have this particular these two different different sort of instruction layout, but like they are still like the same R type. So the idea is that subtype should be able to capture that particular differences. So as I said earlier, like the reason why you are using this schema for us to be able to like unlock automation, and it's also not straightforward, right? The classification is also not straightforward in such a way that we have some like we have it's hard to like create a new subtypes, because while creating subtypes we realize that while working on this we sort of realize that there are sometimes that even it's possible like that some two different instruction sets have the same type, the same subtype, or no, they don't have the same subtype currently as we are the one adding it, but like let's say they have the same structure, right? But sometimes how do we create a subtype from the instruction? So sometimes like there might be like some bits might have the same structure, but they are actually like they have different sort of encoding, different sort of meaning. So how do we classify that? Are we going to lean towards like just the structure alone, or just towards the encoding? So those are the kind of problems that we are facing, and yeah. So and as I said earlier, it's basically an ongoing effort. It's still going on, and still a lot of discussion from different parties trying to see what is the best way to create new subtypes. So it's still an ongoing effort. So thank you very much. Thank you for listening to my talk, and I really want to appreciate RISC-V ecosystem, the mentorship program. So it really like a nice opportunity for me to learn more about RISC-V, and also like to work with to work with the RISC-V community. It's thanks to my mentor Direct, Paul and Foster. They really like they really did a lot of help. They really like helped me out, and I learned a lot from them. So thank you very much, and so you can basically connect with me on my LinkedIn. So thank you very much, and see you.